Do you ever find yourself with complex code that becomes increasingly difficult to work with as the project grows, even after refactors? Does your code look like a mess of bools and if-elses? You might be looking at an opportunity to use the finite state machine pattern in your code. It's a powerful design pattern used all over popular games with the ability to greatly improve your code organization. But wait, state machine, what's that? Well, to understand a state machine, we should first define what a state is. What's a state? Well, think of a traffic light. Hear me out here. It can either shine green, yellow, or red. You could think of a traffic light's color as a state because it can only be one of these options at a time, and there is a relationship between them. When a scenario like this comes up in a game, it's easy to just code up something like var light color equals green to represent a traffic light with a green light. Or worse, a bool for each possible color. You definitely want to avoid bools when dealing with state though, especially complex state, because they are limited to just 2 values. Trying to make several state bools at once can be a recipe for spaghetti that you're not looking for. I like to use enums for simple cases like this, because it's easy to just look up the available states with autocomplete and then check what the state is and update in a match block. But for the sake of this video, I want to show you what this would look like as a really simple state machine. This may seem really overkill for a traffic light sim, but trust me when I say it's powerful in the right use cases, and we'll get there in this video. If you think about it, any set of states can be visualized as a flowchart. This shows us which states can transition into other states. For the traffic light, we know green only changes to yellow, yellow changes to red, and red changes to green again. A state machine is great for when you recognize patterns in state like this because it allows you to organize your logic into bite-sized sections depending on the state. This makes your code much more maintainable and sometimes more efficient, depending on where you're coming from. We can do this separation of state logic thanks to the state class. So the state class's main purpose is to serve as a template for each state's implementation. Here I have a few methods defined. Update and physics update are called every frame. Handle input is for any state-specific input handling. And the onEnter and onExit functions are called whenever entering or exiting a state. We actually don't have to worry about calling any of these methods directly. That'll be handled by the state machine. More on that in a bit. Up here, we actually have an exit signal we can emit to tell our state machine we're ready to transition out of this state. Now that we know about the state class, we can inherit this class in each possible state script, so one for each light state. These inherited classes are where we can put our logic that is specific to each individual state. We can now see we've done away with the match block and if-else statements, with the specific logic for each state separated into their own state classes. But a lot of the times we want to do specific things in our code when state changes. Like when the light changes to green, we may want to run code like this. So knowing that, this will fit great into our onEnter function for the green light state. We can also shut off the green light inside our onExit function. A lot of the time in games there are animations that you'll want to run when entering a new state, and it works great putting them in the onEnter function. Also, you may have some internal signals you need to set up an enter and clean up an exit. Okay, so we've seen a bit about defining our state classes, but how do the actual state transitions work? Here's where the actual state machine comes in. In Godot, our state machine is another class with each possible state attached as a child node. The state machine class has this transition to method that will handle switching states for us. All we got to do is call it directly or emit the exit signal we saw earlier with the state we want to switch to. And that's really the basics of state and state machines. But enough about traffic lights. Let's look at a real game example, something a bit more complex. So I threw together a quick little stealth game using a finite state machine for the enemies. It's a simple little game, kind of like some of those older stealth flash games like The Classroom. So you play as a sneaky square trying to get past all these guards without getting caught. You can see where they're looking with their little vision cones, so you know where to avoid. Alright, so you guys watching know a bit about the game, so I have a little challenge for you. Try to guess how many different states the enemies cycle through. All right, time's up. If you guessed 5 states, you're correct. Good job. Let's touch on each one. So we have the idle state. This state runs when the guards are just chilling, looking around. There's the patrol state when they're walking around their post, the chase state when they're pursuing the player, search when they've lost sight of you, and return when they gave up trying to find you and are returning to their post. Each of these states have their own unique logic, but before we dive into the code for this, let's take a step back. When designing state systems like this, I think it's helpful to set up a quick flowchart so you know what states you'll need and what relationships exist between them. So some enemies will start out idle and quickly switch to chase if they see the player. Then if they lose sight of the player, they start searching for him, checking the last place that they saw him. But if they had no luck finding the player, they start returning to where they were idling. And there are some other enemies that start out patrolling. They will chase the player down when they see him, following a similar path down the state diagram, searching and then returning and then patrolling again. The code is actually very simple once you split it into the states and put the shared logic in the same place. The main thing defined in each state class is the target for the navigation agent to pathfind to and any timers or tweens that run unique to an enemy state. So yeah, that's a more realistic scenario of when you'd want to use an FSM. The cool thing about state machines is that they're very easy to modify. Let's just say our scope suddenly creeps larger and we want to add a new state, shoot the player. Well, we can just hop over to our flowchart again. We just need to add the new state and any connections it has with other states. I figure the guards are only going to shoot the player when they can see him, and right now the guard only sees the player when they're chasing him. So we can transition from chase to shoot when the guard gets close enough to the player. If the guard loses sight of the player or gets out of range, we'll transition to the search state. And that's it. All we got to do is add the new state to the state machine with our shooting logic, then code in any transitions to and from our new state. And here's our new functionality. It's looking pretty good. Repeat this method enough times and you can end up with a finite state machine managing some fairly complex, almost realistic enemy AI systems with several states. It's what games like Metal Gear Solid 5 use for their enemy behaviors. Oh, and by the way, nothing is stopping you from using multiple state machines in conjunction. You can have separate FSMs for the enemy AI and another for their gun, tracking if it's reloading, jammed, or etc. You could even define state machines inside of state machines. For example, a player's state machine could have higher level states like fishing, walking, chopping, cooking, or more, and then substates within those states like reeling in, casting, waiting, adding bait for the fishing state. You can even extend your state machine and define specific transition functions to call only when switching from state X to state Y. For example, you might have to run a specific animation when you switch from flying to landing, and another specific one when going from falling to landing. So after getting this far, you might be thinking, I'm going to use FSMs everywhere now. But I'd actually recommend against that. While powerful, finite state machines aren't the silver bullet for all non-player game behaviors. There are plenty of use cases where you'd make better use of behavior tree or goal-oriented action planning to build a behavior system. In general, those options are usually best for very complex, multi-layered state. Save the details on those for another video if you guys are interested. Personally, I don't think state machines should be used everywhere you see different states. It can actually make your code harder to read if you abstract just a line of code out into a state machine. So if you have just a few simple states that you don't have plans to make more complex, I think you can get by just fine with enums and a match block. But in general, you're probably going to want to set up a state machine if you see more than a few distinct states in your game object, each with their own logic. Here's a few scenarios that come to mind that make me think this could use a state machine. You have boss battles. These are all over in games like Dark Souls. These quickly become complex to implement without a state machine, even simple boss fights. I mean, just think of the numerous states that you could have in a boss battle. The boss could be idle, chasing the player, mid-melee attack, dodging, blocking, teleporting, retreating, healing, dying. And several bosses have multiple phases depending on where their health is at. Also, the enemy AI in the stealth game we looked at could have plenty more states added. They could have a state for changing station, investigating noise, attacking the player, checking the last place the player was seen, dying, fleeing, talking with another guard. Heck, even the enemy's guns could have their own state machines, tracking things like if it's ready to fire, it's jammed, reloading, and more. You could even use an FSM in a multiplayer lobby setting to track player connection states, like waiting, loading, ready, in-game, offline. I mean, I could keep going on, but I think you guys get the gist. There's plenty more use cases in and outside of game programming for finite state machines. They can make your life so much easier. So I hope you learned something from this video. Please leave the video a thumbs up and subscribe if you enjoyed and want to see more. I'll see you guys in the next one. Thanks for watching.